Probability, what does this mean? Let's do A and B in general. Let's keep it general. This is and, okay? And is your overlap in a Venn diagram, or is everything inclusive?
I did this wrong.
And is your overlap. So what's the probability that you like M&Ms and Skittles, both?
Going
You know everything you need to know.
0.08.
0.08, right.
Oh,
You
okay.
just add up the overlap, right?
Oh, that was a good guess then.
Yeah, you just add up the overlap. What's the probability that you like M&Ms or Skittles?
0.65.
How'd you get it?
The whole circle of M&Ms plus the rest of the Skittles circle.
Yes. Exactly. Just making sure you added the overlap. Because it's everything. The or is everything, including the overlap. Okay, is everybody okay with that?
Hold on a second.
Sure.
Yeah, that's good.
Okay. What if I give you the information? Where do you start to build your Venn diagram? In the center. And then you've already counted that part, right? So you have to subtract anything else away. And everybody pretty much got that right on the re-quiz. So are we all okay with that? Okay. Okay. Where did you put the, oh, okay. I was gonna say, where'd you put the iPad? Okay,
I'll make sure it doesn't like turn off.
I'm gonna move it out of its range, I'm sure. All right. So are we good with the basic stuff here? Okay. Now, if I have more than one event occurring, then the probability of A and B happening is the probability of A times the probability of B given that A already happened. You don't really need this formula either at this stage because you mostly know this. If I give you your bowl of Skittles, what other color of Skittles are there? Green?
Red, green, blue.
Okay. And I say, what's the probability that you pull out 2 green Skittles without replacement? What are you going to do? How many green Skittles on the first round?
10.
Out of?
I guess that.
This time I wasn't
15
nice.
plus 10. Sorry?
23.
23.
Okay, this time I wasn't nice to you. I didn't pick pretty numbers. Okay? Then the second time, we've already eaten the green one we just pulled. So now, how many green ones are left? 9, and how many Skittles are left?
22.
Okay? And so you actually know this automatically that what's the probability of getting a green Skittle times what's the probability of getting another green Skittle given you already got a green one. So you kind of know that formula innately from the things we've been doing. Okay? Questions about that kind? Okay, now, the way we do use this formula a lot, the second one, is this. We rewrite it to be this. Okay, we rewrite the formula to get the probability of B given A is the probability of A and B divided by the probability of A by just dividing both sides of this formula by the probability of A. That's the way it's given to you on the formula sheet. You see it that way because that's how we use it all the time.
Okay, because it goes perfectly with this part. Will we take this part out? Because I normally dramatize this perhaps in it just when you get to the time. That,
Yes.
Then it gets a little funky.
So is that basically like when you see something and you lessen the pool for it because it says, like instead of out of the whole school, say like out of the CGS kids, how many applied
Correct.
to VC or something like that? So it
Right,
just
so
lessens the pool.
we're going to come back to this table right now, okay? I can do that formula without actually doing the formula here. There are lots of times I need that formula, but here I can do it without the formula by saying, what is the probability that you gave books given that you were in English 10 class? Okay? The minute you have a given condition, you may only pick from that pool. So Robbie, how many are allowed to be picked from to meet this condition?
English 10,
Just the English 10, which is how many?
14.
So my denominator is now, out of those 14 English 10 classes, what percentage gave books? So 10. So this is A and B gave books and are English 10, and this is English 10. So you're using the formula, but you really can kind of figure it out. Again, for this kind, the trees, you've got to have the formula. But for this kind in the table, you can kind of figure it out without the formula. Okay? What's the probability that you are English 10 given that you gave no books? So what am I asking you now? Who am I allowed to pull from? Who am I checking in with?
The people that brought notebooks.
The book, yeah, how many classes brought no books?
12.
So out of those 12 classes, what percent of those are English 10?
4.
So it's
So a third, right, of the classes that brought no books were 10th grade English classes.
What a disappointment.
Exactly. It's a good thing we didn't check on the freshmen. Where half of them didn't bring any books. Or that's not right. Half of those who brought no books were freshmen.
what would it be for seniors, like if they're the seniors in there?
0.
It depends whether they're trying to get rid of their books and clean out their room, or if
Y'all
they
should
just...
give books.
Giving away the school books.
Do they? I'm going to ask a question that has nothing to do with the review people out there on TV land. Used books or new books?
Preferably used, because then you don't have to go out and buy it.
Okay, so it's okay to do used books? Because I'm going to go through some of our used books, I think, and bring them. And it's any age, right?
It's any age this year,
Okay.
because we.
Should throw in
last
our
year-
box for seniors.
Where's your senior box? I've seen
It was
the-
like
Is it in
just
there?
kids
I've
for
seen the,
classes.
one's Meyer and one's Olson, right?
Yeah, I think ours is in there.
I will split them evenly because I teach everybody, so half of them will go in the Olson
you
box
teach
and
us
half will go in the
more.
Meyer box. No, I teach probably as many 10th and 11th graders. Maybe I teach more 10th and 11th graders together than I teach. I can do it proportionally
Oh my gosh.
based on my number of students I teach in 10th and 11th versus the number I teach in 12th.
That might require a lot of books though.
And we're leaving.
It might.
I mean,
I'm
not necessarily a bad
leaving.
thing.
Okay.
but-
All right, back to the review. Back to the review. All right, we're going to come back to that formula in a minute, but in the meantime, I want to talk about this. Give me another word for mutually exclusive. Yes, that's correct, Allie. Finish it off.
Independent.
No.
Not
No.
discrete.
Starts with D.
Indiscriminate?
No.
Indiscreet?
Starts with a
Connor,
D.
do you know?
Can we go like the next
I don't
letter?
know.
What?
Is the next letter an I?
It is D.
Differential.
No.
No.
What's
I don't know
the
why I
letter
said
after
that. Disjointed.
Disjoint.
I was like, what?
Not overlapping. Separate from each
I
other.
don't know why
Disjoint.
differential.
Completely.
Okay? The picture looks like this. The math looks like this. Okay? If they are mutually exclusive, they cannot both happen at the same time. It's one event, they cannot both happen at the same time. The probability of them happening at the same time is 0. Okay? If I have if I ask you what is the probability of getting a 7 on a red die, if let's say I have a red die and a green die, okay? No, that's not what I want.
Probably
Let's say, what's the probability, if I asked you for something like the probability of a red die giving me a 3, and a green die giving me a 2, when I rolled them both, I would be fine, right? I could get that.
That's multiplication.
Yeah, there's one way to get that. Roll both die, right? There's one way I could get a red 3 and a green 2. Okay, so that's not disjoint. Okay? But, is there any way to get, on a single roll, is there any way to get a red die to give me 3 and 2 at the same time?
No.
No, so those would be mutually exclusive or disjoint. Yes.
And then, disjoint cannot be independent
Correct.
because independence implies that that doesn't change probability, and mutually exclusive such disjointness implies that there's that when you have one, you can never have the other, which changes the probability from whatever it was to 0.
Absolutely. You got it. We'll talk more about what he just said.
Thank you.
he rambled through it very quickly, but we'll talk more about it.
That sort of thing.
Yes. Okay. Independent
Well, that
means
should be a
that the
superpower.
probability of A, given that B happens, okay, is exactly the same as the probability of A happening. Mathematically, that's what independent means. That it doesn't matter whether B happens or not. I get the same probability all the time. Make sense?
Yes.
Okay,
What-
so for example, I flip a coin, all right? What's the probability of getting a heads? 0.5, okay? If I flip a coin again, what's the probability of getting a heads?
Still the same.
Still 0.5. Does it matter whether my first flip was a heads or a tails?
No.
No. So, unlike this case, right here, okay, where the probability of getting a green Skittle was 10/23, but the probability of getting a second green Skittle is 9/22. So, the probability of green changes if I assume I got a green the first time. Okay? It actually changes whether I got a green or not the first time because I didn't replace the Skittle. I ate it. Okay? These are not the same. They are not independent events. You have changed the probability by pulling one out. But the probability of getting a heads is exactly the same of getting a head the second time, whether or not I got a head the first time.
So
Yes.
independence requires replacement. When
Yes.
you're drawing from something?
Yes.
Gotcha.
Okay? If you're drawing things, independence requires replacement. And so if I had put my M&M back in and not eaten it,
Which would be weird, but yeah.
which would be very weird, okay, then I would have had independence. Because I still would have had a 10/23 chance of getting a green the next time. Okay? Now eventually, we've done a couple problems here. Oops, I didn't mean to erase the formula. If you pick a large enough population, okay, and that's how we handle the fact that it's really hard to prove independence in the population as a whole. When we go to do all our tests and stuff we run at the second semester of stats, we basically say we have to be big enough that it doesn't change the probability enough to matter. In other words, if I had 20,000 Skittles, okay,
That one might feed this room
Right.
for like a week.
and 10,000 of them were green, and I pulled
Are you leaving there?
and I pulled a green one out. I don't particularly eat it. I'd much rather have chocolate. Okay, and I pulled a green one out. The probability is a half. 10,000 out of 20,000. Right? I ate the Skittle. I pull another green one. Okay, now my probability is 9,999 out of 19,999, which in essence is, if you do it on your calculator, a half. It's like 0.4999999. Okay? So we haven't really changed the probability enough to matter. So we say we're okay to use our independence assumptions that we need later on, even though we don't truly have independence. Yes?
Does this explain why the ideal polling size is around 3,000? Because
It is definitely part of it.
Okay.
I think there are some other factors that go
I'm
into
sure.
that. But yes, it is definitely part of why they have polling sizes that are a certain size. Okay.
independence.
It's because we can't really always prove